Welcome to the Explainer. We're jumping right into what I consider a critical tactical briefing today. We are building a Triband tactical MANET, engineering a multi-layer off-grid comms node specifically for voice, video, and text. Look, we're talking about maintaining high-bandwidth data in the most demanding, rugged environments out there, completely independent of commercial infrastructure. No cell towers, no problem. So let's deconstruct this node piece by piece. Our agenda for today. First, the tactical comms dilemma. Second, the Triband architecture overview. Third, decoding the 3 radio layers. Fourth, smart routing and zero crosstalk. Fifth, the field hardware build. And finally, number 6, unbreakable autonomy. Let's get into it.
Section 1. The tactical comms dilemma, or what I like to call the trade-off trap. Okay, let's dive into this.
This is the exact core problem every network engineer eventually faces in the field. It's a massive trade-off. Trap. On one hand, you've got high-speed 5 GHz Wi-Fi. It gives you blazingly fast data transfer, which is awesome, but it gets instantly blocked by walls, trees, you name it. On the other hand, you have long-range solutions like LoRa operating at 915 MHz. Now this punches through obstacles and gives you literally miles of coverage, but it is painfully slow. We're talking capped at around 2 kilobits per second. So when you rely on a single radio node, you're forced to choose. Do you want to stream high-bandwidth video, or do you want multi-kilometer range? You can't have both. Which brings us to a massive, high-stakes question. How do we actually maintain high-bandwidth comms in off-grid environments without sacrificing our range? Well, if a single radio is our failure point, the ultimate solution is staring right at us. We just have to eliminate the single radio failure point entirely.
Section 2. Triband architecture overview, the brains of the node. So, how do we build this? To kill that single point of failure, we're shifting our entire approach to a Triband architecture. We're building a 3-tier, multi-frequency mesh node designed specifically to segregate traffic across 3 completely independent wireless bands. It all starts at step 1 with our core compute, which is a Raspberry Pi 4B running OpenMANET. From this central brain, the architecture branches out. Step 2 is layer 1, handling our high-bandwidth 5 GHz traffic. Step 3 is layer 2, operating in the sub-1 GHz space. And finally, step 4 is layer 3, pushing ultra-range telemetry at 915 MHz.
Section 3. Decoding the 3 radio layers, anatomy of the mesh. Let's peel back these hardware layers.
We're going to start with the high-speed superhighway and work our way down to the off-road emergency trail. First up, layer 1. We're using the Alpha AWS 036 ACM with the MT7612U chipset. This is a dual-band 802.11ac radio, acting as our short-range, high-speed backhaul. When I say short-range, I mean a 100 to 300-meter link. Its job is to push the really heavy traffic, HD RTSP camera streams, Jami video calls, huge bulk file transfers. And because it has native Linux support, you get 802.11s mesh support right out of the box. It is incredibly powerful for close-quarters data dumping.
Now, if layer 1 is the superhighway, layer 2 is your reliable state road. This is the Wi-Fi HaLow hat from Morse Micro, a sub-1 GHz 802.11ah module. This layer handles the long-range IP backhaul, giving us about 1 to 3 kilometers of line-of-sight coverage. The absolute game-changer here is that it punches right through thick concrete and dense foliage where your 5 GHz signal would just instantly die. That makes it the perfect layer for ATAK voice push-to-talk, high-res map syncing, and sending compressed 480p video streams.
And finally, we hit the off-road emergency trail, which is layer 3. This relies on the Heltec V3 and SX1262 LoRa radio operating at 915 MHz. This is your standalone, ultra-low power fallback layer that can reach anywhere from 5 to 15 plus kilometers out. It's meant for sending critical emergency telemetry, things like GPS location coordinates, cursor on target map markers, and short texts. But here's the massive architectural advantage of layer 3. It connects directly via USB or Bluetooth. It operates completely independently. So even if the Pi's Wi-Fi network suffers catastrophic interference or completely fails, this layer stays alive to get your data out.
Section 4. Smart routing and zero crosstalk, the intelligent network.
Okay, so with all 3 of these radios packed into one node, you're probably wondering, how does this not turn into a chaotic, interfering mess? The secret sauce is the software running behind the scenes. Enter BATMAN-adv, which stands for Better Approach to Mobile Ad Hoc Networking. This dynamic network manager is absolutely brilliant. It literally takes our high-speed alpha adapter and our long-range HALow module and seamlessly combines them into a single, unified virtual adapter called BAT0.
Let's walk through a real, mission-critical scenario to see this dynamic path selection in action. Imagine your node physically moves behind a dense obstacle. Instantly, the network's transmission quality, or TQ metrics, detect a drop in that 5 GHz signal. But before your video feed can completely drop, BATMAN-adv executes an instant failover, smoothly routing your traffic down to the sub-1 GHz HALow layer. It automatically routes the heavy stuff when nodes are close and fails over instantly to avoid network death when they separate.
This perfectly illustrates how we achieve true zero crosstalk. We are intentionally mapping specific traffic types to dedicated hardware and distinct frequency bands. High bandwidth video? That floats through the alpha at 5 GHz. Voice push-to-talk? That goes through the HALow at sub-1 GHz. And your text or location data is routed through the Heltec at 915 MHz. Because we're operating across 5 GHz, 900 MHz Wi-Fi, and 915 MHz LoRa, we completely prevent radio self-interference. Real-time, simultaneous execution without any of the layers stepping on each other's toes.
Section 5. Field Hardware Build, Ruggedizing the Node.
All right, so we understand the digital brains and the radio frequencies. Now let's visualize assembling this tactical schematic into actual physical field hardware. First, the whole shebang is housed in a weatherproof Pelican or Nano enclosure, rigged with external N-type connectors. For your antennas, you're going to pair dual 5 dBi Omni antennas for your high-speed 2.4 and 5 GHz backhaul. Step up to a high-gain fiberglass antenna to punch through the environment with your sub-1 GHz HALow, and finish off with a tuned whip antenna for the 915 MHz LoRa layer. And obviously, to keep this node alive off-grid, power management is crucial. You'll want to build this out with a robust 12-volt LiFePO4 battery pack, paired with a step-down converter delivering a clean 5-volt 5-amp USB-C power delivery.
Section 6. Unbreakable off-grid autonomy. Mission success.
When you combine that Triband architecture, the smart routing software, and a ruggedized physical build, you achieve one incredibly powerful result: graceful degradation. Honestly, if you take only one thing away from this explainer, let it be this concept. Thanks to this multi-layer design, if your physical environment degrades, your network degrades gracefully right along with it. It seamlessly scales down from pushing HD video on the superhighway down to IP voice on the state road, all the way to sending a critical LoRa text on the emergency trail just to ensure your communication survives. It gives you total off-grid autonomy, zero reliance on cell towers, and it's all achieved with incredible cost efficiency using open-source tools. We're literally engineering a network that simply refuses to die.
I want to leave you with a final thought here. The tools to build these unbreakable communication nodes, they are entirely accessible to us right now. Utilizing off-the-shelf consumer hardware and open-source software like OpenMANET, BATMAN-adv, and Reticulum, the power is literally in your hands. So the question is, are you ready to deploy decentralized open-source MANET infrastructure in your own tactical operations? The blueprint is right in front of you. Thanks for joining me on this explainer. I really hope it sparked some ideas for your next build. Keep experimenting, and I'll see you next time.